Yes, so hello and welcome students. So let us start today's lecture. MA415 Algebra. Okay, and this is lecture number 30. Okay, so now recall we are discussing about this relation among these special type of rings, right? And then we proved, recall that in last lecture we proved that ZX is not a PID, and this is UFD that I ask you to, but is an unit factorization domain. You can easily prove this thing. This part you can prove. Okay. And the second part, we discuss a very special type of ring 1 plus 2 minus 19 by 2. And we show that is a PID, right? Because it has a norm that guaranteed that is PID. Okay, but then this was also an example that I can just say that z 1 plus 19 by 2. So suppose this is my ring R is not an Euclidean domain. So obviously there are many ways to prove this thing. Okay, I will give a proof, maybe one or two proof. Okay, but let me just discuss some simple question first. So this is maybe homework, you can easily do it. So like find out all the units in z of 1 plus. Okay, and the answer is let me tell you that there are the answer is 1 and minus 1. These are the only units in the ring z1 plus 2 minus 19 over 2. Okay, find out that if something, see, 1 is a unit obviously, 2, and if something is a unit, then what happened? Okay, you can find it out. Okay, and maybe one more question. What about the element 2? See, element 2 and 3 is always there, right? This is contains z, so the 2 and 3 are actually irreducible in this ring. So let me write down R only, okay? Otherwise writing again and again z to the power 1 plus 2 minus 19 by 2 is taking more time, right? So in this ring 2, 3 are irreducible. You can just do this homework, and these are not so difficult, but the process may be lengthy, you need to calculate. Okay, like for example, if 2 is reducible, then what happen? You write down this is a product of two elements, and take norms, like the norms you defined last time, right? Taken as a norm, and whatever that field norm. Okay, and then find out there is a contradiction. So this is possible. You can always find out this irreducible. Okay, so now we need to show that that R does not contains any Euclidean norm. That we will show that instead you don't have a Euclidean norm. Okay, so this claim that this ring Z 1 plus minus 19 by 2 does not have a Euclidean norm. Okay, so what does that mean? That means cannot be Euclidean domain, right? because to be a Euclidean domain, it must have a Euclidean norm. Okay, now a proof. So you can assume the contradiction. So and then find out method. So we'll prove by method of contradiction. So we will prove this by the method of contradiction. Okay, method of contradiction. Okay, so what does that mean? That means we assume that there exists Euclidean norm. Then what happened? Okay, so let n be a Euclidean norm. Euclidean norm on R. Okay, so what does that mean? That means you can do Euclidean algorithm with that conditions that you can find out for every two elements be non-zero, then, right? Okay, so now what I am doing, I just want to so I know that you have two units only here, +1 -1. So I just want to write down this set S, which is or rather I must say, okay, maybe S is my R minus, you just remove 0 and this +-1 element. So I know, see, for units the norm will be always 1, right? So I don't care. So S is all those elements which are obviously non-zero non-units elements, right? Now we want to find out say S dash, which is actually norm of all the element of A such that A belongs to S. Okay, so non-zero element, we take the units, right? And obviously this is a substitute natural number. So by Wheel ordering principle, Wheel ordering principle, there exists B belongs to that S such that norm of B is then norm of A less than equal to, I must say, norm of A, because E can be B for all A belongs to S. Okay, and obviously see this cannot be 0 or 1, this norm, right? Because they are units. So there are least possible numbers. Okay, so B is a number and I can play the division algorithm with respect to B. So what I can do, I can check, for example, if I have to use the division algorithm for 2, then you can write down 2 is equal to some QB plus R with because you have a norm, so R is 0, or this norm of R is less than norm of this B, right? Clear? So okay, yeah, so what happens if R equal to 0? So if the case, if R equal to 0, then what happens? Then your 2 will be equal to Q times B. What does that mean? That means that your B divides the 2, and what are the options? Because B divides 2 and 2 is irreducible element, right? So this implies that your only options for B is +-2. Only these are the elements. Now if R equal to C, and the other case that norm of R less than norm of B, right? But see, the B I choose the least, B is the least among the norm of the elements which are non-zero non-unit. And if R is one of, if R has norm less than that, then R has to be either 0 or unit, right? but r cannot be, I mean for r0 I know I got it, so this implies r equal to say plus minus 1, right? If this and r not equal to 0, then r has to be plus minus 1. If r equal to plus minus 1, then what happens? Then you see b divides either 3 or b divides either 1, but 1 is not possible, right? Again, so because 1 is a unit, right? And I choose b is non-unit, right? So then what happens? So then r equal to say minus 1 implies your b divides 3, and this implies b equal to plus minus 3, right? R cannot be 1 because so if r equal to 1, then b into q equal to 1, but that is not possible. B is not a unit, right? Okay, so b equal to plus minus 3. So the minimum element has 4 options, plus minus 2 or plus minus 3. This is the minimum element, right? Okay, now I choose another nice element. Now for say, let me choose that x equal to that the generator, that special element 1 plus root over 1 is 19 by 2, and I can play the game, right? Because I assume that this is the Euclidean domain, Euclidean norm. So if I play the same game, then I have this equal to something, some q1 times b plus r1, right? And again the condition r1 equal to 0 or norm of r1 equal to less than norm of b. Okay, but I know that for b there are only 4 options, either plus minus 2 or plus minus 3. This is known to me. So so what does that mean? If norm of, so that is b divides either, see when r equal to 0, b divides either this x, or when r equal to, say when norm of r1 less than norm of b means when b equal to say plus minus 3 or plus minus 2, and then what are the options? Then this means the r1 has to be plus minus 1 here, right? And in that case option is that b divides either this or this. This or this. Okay, for first case you will get b divides x, otherwise you get b divides x plus 1, x minus 1. These are the only options, right? And now b equal to plus minus 1. Now you see that neither of this but this plus minus 2 or plus minus 3 does, I mean they do not divide this 1 plus 19 by 2 or whatever, plus minus, doesn't matter. Okay, if you add plus 1 or, right, they don't, so this is not possible, you see that? Okay, so they don't divide this element, right? Because if they divide, then this the element will be not inside Z of this, the quotient will be inside Q, right? Coefficient will be coming from Q, that is not possible, right? So they don't divide the and so this is a contradiction. So that means what? That means yes. Oh my god, what is happening? Something is happening here. Yes. Okay, yeah. So thus we have a contradiction Dixon, and hence R does not have any Euclidean norm. Okay, and this is the proof that this is not Euclidean domain. Okay, so this is one way of proving that thing, and obviously there is another way of finding the case where okay, so yeah, so another way of finding a case that something is a very basic important property of Euclidean domain. So this is ends, the proof ends here. Okay, so in Euclidean domain there is a very important property holds. It contains something called universal side divisor, and I would like to tell what is that. So what do you mean by universal side divisor? That we would like to define. Okay, so let me discuss this issue. So so let R be an integral domain. I can define for integral domain actually. Integral domain. Okay, so a non-zero non-unit. See, remember here I need it has to be non-unit also, because unit means unit can reverse everything, right? Because the inverse exists, so we can so you can write down, right, everything by so a non-zero non-unit B belongs to R is said to be a universal side divisor. Universal side divisor if for any A belongs to R, A belongs to R, we have you can have that A can be written as something called QB plus R, like almost division algorithm, but like with little bit different, with R is equal to 0 or unit. See, remember in the definition of Euclidean norm, we define say the R equal to 0 or norm of R is less than norm of B, right? But here I am saying that it is unit. So this is kind of trivially I am telling that every Euclidean domain contains at least one universal side divisor, right? I will give you a proof. Okay, so universal side divisors are what? Universal side divisors are those such that so first of all, there has to be non-zero unit, and whenever they choose some elements, either that they divide the element when R equal to 0, or they divide and side means what? So A minus R is divisible by B, right? And R is the unit. So you are kind of you are just translating A by an unit and then it divisible by B. So this is the property, and this property is actually is true inside an universal Euclidean domain, but this is not true inside the principal ideal domain. Maybe I will show you. Okay, so I can write down the theorem. So so let R be an Euclidean domain, which is not a field. Okay, because in field you don't have field everything, even on your elements unit, so you cannot find out this, right? So not field, then R always contain universal side divisor, universal side divisor. Okay, so universal side divisor always exists inside Euclidean domain. And then how do you prove this thing? So again, the proof is almost similar. The idea I just give you sometime before. So let n be an Euclidean norm. Okay, so remember one thing, or rather, I think, yeah. So should say Euclidean, not an. Euclidean norm on R. Okay, and I am interested to know what is the minimum element. So I should not say what is the, because there may be many element having minimum norm. Okay, so what I'm doing too, so I'm writing S as norm of A such that A is not 0, zero and unit, not unit. Okay, so I'm taking all the non-zero non-unit element and then taking the norm of those elements, right? So this will be again because of the norm map to natural number in 0, but I just remove 0 part, so it is subset of natural number. So again you can find out that ordering principle. So by well ordering principle, let us choose, so you can find out or whatever that B belongs to that R with I mean R means non-zero non-unit, I should say. So R minus, okay, so here I must say something, different symbols. So let me write down the symbol by this. So you have R and then you have minus units, union 0. Okay, with norm of B is the minimum. Okay, with norm of A for all A belongs to R minus this. Okay, now I'm claiming that see well-known principle guaranteed this kind of element, but it never guaranteed that is unique. Okay, so what does that mean? There might be many elements with the same property. Okay, so whatever, I don't care. So if I have one, then what I have, then I can use now for any say A belongs to R, you can write down A equal to QB plus R, right, with r equal to 0, or this norm of r is less than norm of b. So what does that mean? That is r is a unit, right? Because if it is a non-unit element, a non-zero element, then the norm cannot be less than norm of b, because it is the least among those norm of non-unit element, right? So this is a proof. So you can always do this thing in a Euclidean domain. Okay, and the interesting part is that these proofs also prove that the Dedekind has a norm, what we have discussed in last class. Is actually not an Euclidean norm. Okay, so the corollary the Dedekind has a norm on Z mod 1 plus or minus 19 by 2 is not Euclidean norm. Why is not Euclidean norm? Because if it's Euclidean norm, then you have a universal side divisor, right? So you can easily find out. You can easily. I mean, let me give some idea. Then you can easily prove it. Okay, so how to prove this thing? So on the contrary, let us assume that this norm, this Dedekind as a norm. You remember what was the norm? What was that norm? That norm in the sense a plus b times 1 plus the power minus 19 by 2, and that 2 is square plus a b, remember, plus 5b square. Now this is Euclidean norm. Let us assume that is a Euclidean norm. Then we will find out a contradiction. So what does that mean? That means if the Euclidean norm means you must have a universal side divisor, right? So let choose a side divisor. So let B be a universal side divisor of R. This R means Z1 plus the power minus 19 by 2. Okay, now if it is universal side divisors, then what happens? If you find out a universal side divisor, then okay, okay, first of all, I will now so again, in the by definition, whatever element you choose, you can always do it like the same way I did. That B universal side divisor tells you that B will be kind of like the proof I gave, that this is not a PI and not a UFD, right? Sorry, not a ED. Then proceedings. Okay, I'm not giving a proof of a proof because I have given idea before. So then in the choices of B will be what? This is plus minus 2 and plus minus 3. Okay, that I already give it in the proof. And So what does that mean? That means again that you can prove that this 1 plus 19 by 2 um, does not satisfy, does not uh, satisfy the definition of the universal side divisor, right? Universal side divisor, right? So if you divide this x by b, so it's not possible. So x by x, so x, so how do I write down? I should write down like this. So b cannot divide x in z of 1 plus 2. Either b cannot divide this, or whatever, x plus 1 and x minus 1. These are the only possibilities. We cannot divide those, right? So this is a proof. I mean, this you can also prove by like these two, so that this is not in Euclidean norm. Okay. So so there are many such problems which are which you can prove similarly. Okay, so maybe I will discuss one more nice observation, and maybe we will, let's see. Okay, so what we learned. So you have among the relation, you know how to find out all those so we will now discuss one important remark, and then we'll give a proof, maybe to end these things. So what can you say about the primes which divide some nice integer, nice form? Okay, so for example, if you see that I mean, choose say 5. Okay, so you see that 5, I mean integer, integer 5, for example, it's 13. Okay, so you see that these are actually, or maybe 10. Okay, so oh no, 10 I don't need. So okay, so for example, you choose any integer of the form, say n square plus 1, right? 5, 13, or maybe yeah, 10 also you can write down, no problem. 10 also, yeah, 10, and then 4, 17, then 26. Okay, this kind of integers. So this integer of these forms, and you see that the nice property of this kind of integer, that you have a prime that divides these kind of integers, having a nice property. So let me write down this as a theorem, then you will have more understanding. So so let I don't need to let yeah, so you can say that a rational primary, like a prime in z, a prime in z divides an integer of the form say n square plus 1 in z That is true if and only there are two cases. Either obviously p equal to 2, because p equal to 2 it will give you p equal to 2 will gives you 1 square plus 1, which is 2, right? Or p is congruent to 1 mod 4. Okay, p is congruent to 1 mod 4. This is in fact you can have a more general theorem, but that is out of our reach. In this we need to understand some kind of algebra number 3 for that. But I don't want, I just want to show that this is, for example, 26 is of this form, right? And you see that 13 divides 26, right? And 13 is of the form 1 mod 4, right? Prime of the form 1 mod 4. So how to give this kind of proof? So this is if and only condition, no? So you have to prove two things, that if if this is of these forms, see the case, this is trivial, 2 always divides 1 square plus 1, right? So this is trivial, right? So for non-trivial, what you need to prove? You need to prove that so suppose 2 divides the p divides n square plus 1, okay, and I will prove that p is congruent to 1 mod 4, okay, and p is odd, obviously, because for even case it is the only case, right? There is only one even prime, okay. So in that case, if I have to prove that p is actually congruent to 1 mod 4, how do I prove? So what does that mean? So this implies that n square is congruent to minus 1 mod p, right? So what does that mean? That means when you go modulo p in z mod pz, this order of n equal to 1 in z mod pz, right? Because n square equal to order of n equal to 4, what I am saying, order of n equal to 4 in z mod pz, because n square equal to minus 1, so n to the 4 equal to plus 1, and that is the least positive integer such that order the power equal to 1, right? This order is 4 in z mod pz. So what does that mean? That means that you have an element of order 4, right, in z mod pz. If p divides n square plus 1. So but we know that order of n, but order of z mod pz, what is the order of, or rather I should say star, yeah, this is multiplicative group, right? Multiplicative order, yeah, z mod pz star. So order of z mod pz star equal to p minus 1, right? Because except 0, every other elements, if you choose, they forms a group with respect to multiplication. So order of this equal to p minus 4, and we know the order of an element divides an order of the group. So thus 4 divides order of the group p minus 1, and this implies p is congruent to 1 mod 4. This is the one part of the proof. Now conversely, let us assume what I want to assume. I want to assume that I have a prime p is congruent to 1 mod 4. Okay, and I have to prove that p divides an integer of the form n square plus 1. Whatever prime you choose, if it is congruent to 1 mod 4, it must divide an element of the form n square plus 1. Okay, so what does that mean? So I will find out some nice elements. So let me do it. So this implies that 4 divides p minus 1. Okay, and so p minus 1 is what? P minus 1 is actually order of z mod pz star, right? But z mod pz star is what? Z mod pz star is abelian group, actually. I mean cyclic group. So So you can either say that I mean, see, you can easily say that the cyclic group, so every subgroup cyclic, and hence if you know that Z mod PZ star is cyclic, then the proof is simple. Is a cyclic group and hence it has a subgroup, rather unique I must say, but it's okay, subgroup of order 4, right, which is isomorphic to Z mod 4 Z, right, because all the subgroup of cyclic group is cyclic, so we have a subgroup, right? And what does that mean? That means that it has an element of order 4. That's the important things, because the subgroup, cyclic subgroup order 4 generated by a single element, that is order 4, right? So what does that mean? That means Z mod PZ star contains an element of order 4, right? Say, let me write down, say M. So thus, what does that mean? Thus M04 is equal to 1 mod one. See, so this is in Z mod P just star, so mod P, it is this, right? So what does that mean? That means M square is minus 1 mod P, and this implies P divides M square minus 1, right? Which is we want to prove that P divides, so this completes the proof. So P divides an element or integer of the form M square plus 1 or N square plus 1, whatever. Okay, so this is one idea, but you can actually prove much more thing, something called Fermat theorem. You can say that the prime, which you can write down sum of 2 square, like you have a square plus b square, and what are the primes of these forms, and then you can say that either p equal to 2 or p equal to congruent to 1 mod 4 actually. And this theorem is called sometimes Fermat, is due to Fermat. Okay, like the proof is you need some techniques from algebra number theory, so I'm not writing, so Fermat. That so a prime p is of this form, a square plus b square. Okay, a b are rational integers. Okay, if and only if you can write down either b equal to or in fact you can say more, you can, so no, I think this is, you can actually prove without no, I need some techniques, but let us just tell these issues here. RP is congruent to actually 1 mod 4. Okay, in fact you can say more, actually you can say that much more general thing, that n is congruent to a square, n equal to a square plus b square, if and only if p divides so there does not exist any prime p is common to 3 mod 4, and that divisor must be of order odd order. Then this cannot happen. So how do I write down? So let me write down in and so you write down say p1 power alpha 1 p k power alpha k. Okay, so if some say pi equal to 3 mod 4, this is pi 3 mod 4, this kind of prime, then this is finally actually this alpha is even number or even integer. For example, it cannot be the all integers powers which divides n. Maybe I will give an example, then you will understand. So let me construct an example. Yes. So you see that 3 square plus 6 square, which is 45, right? So this is of the form a square plus b square, and this n actually divisible by what? So this 45 you can write down as 3 into 3 into 5, right? Okay, now there is no problem because this is congruent to 1 mod 4, and this prime is prime congruent to 3 mod 4. But you see the power is even integer. What I am saying, even integer. It cannot be odd integer. It's like if you have 3 cube into something, whatever, you cannot write down this of this form. Never. Okay, this is not possible. It's not possible. But this requires some techniques of algebraic number theory, so I am not going into details. Okay, so with that, maybe I will stop here the discussion with this ED, PID, and UFD, and maybe I will discuss little more in next class on irreducibility over polynomials. In polynomials, ring, what you can say, like those are UFDs. In EFDs, can you say the irreducibility coming from something called field of fractions? So those questions we'll discuss. Okay, so let me stop here now.